Okay, so we're now going to be talking about potential energy. And sorry, I started the live stream late here. Give me just a second. I got to hit pause on here. So it takes about 20 seconds to buffer. Got that. Let me get back into my Zoom meeting. Thank you, Asai, for reminding me of that. I just forgot. That's why I don't like to stop the live stream halfway through usually. Where were we? We're right in here. All right. So just a quick reminder. So it's in there. We're going to talk about conservative forces, gravitational and spring forces. They do no network on any closed path. A closed path is one that starts and stops at the same point. Now, the definition here, we're going to define change in potential energy as negative work. So again, the change in gravitational potential energy is opposite the work done. So again, in this case, we were just talking about the forces. Sorry for a little bit of a repeat here. I see that the change in y, or the vertical displacement, is negative h in the j hat. Got it. I see that the force in this case is negative mg in the j hat. Now think about it. The force is pointing downwards. You move downwards. We expect gravity should do positive work. Gravity should speed you up as you go downwards. Gravity slows you down on the way up, speeds you up on the way down. So that's why inside of here, the work done is positive. This minus sign out front is from the definition. It's from this definition right here. Okay. Any questions on that? Okay. Now, notice this next statement. We are given a choice. Just like you could choose whatever coordinate system you want, we could choose whatever height we want to be y equals 0. For example, I could say the top is y equals 0. And if I did that, the bottom would be height y equals negative h. Right? So the vertical position may be different numbers, but the change in vertical position, delta y, is always going to be the same no matter what coordinate system you use. So notice the change in potential energy should always be the same as well. That said, generally speaking, unless you have some good reason to do otherwise, and we will encounter one possibly today, unless you know otherwise, set y equals 0 at the lowest point in the problem. This just reduces the number of minus signs. So by setting this equal to 0, right, what I could see here is this result. This allows us to say the potential energy associated with gravity is given by mgh, where h is the height above a reference level. All right, now more on that later, but any questions about what I'm showing you here so far? Again, it's just like coordinate systems. You can call 0 wherever you want, and you call the lowest point in a problem 0, so that all the other heights, to get the gravitational potential energy, it's just mg times the height above 0. Notice the subtle difference. Okay, let me just write this on the board. To be clear, notice there's a difference between u, which is mgh, and that's height above, I'll say, reference level, and delta u, which is equal to mg change in y. So here's the interesting part. These numbers mean nothing. Absolutely nothing. What matters is a change in u. This is the quantity that has physical significance. This is the quantity that relates to work. This is the quantity that's the same in every single problem, no matter where you put your reference level. Now, over here, what does matter is you could see for any particular problem, you could see for a given reference level, the bigger the u, the more, basically, the higher up you are. But in general, you could say 0 equals the moon. And then heights from Earth to the moon would all be negative. So the particular numbers don't mean anything. What matters, what is physically meaningful, is the change in you. All right, enough on that. We'll get into these problems in a minute and see what matters and what doesn't then. All right. In chapter 14, we'll talk about this and how to do astronomical things. Now, I want to make a note here. This is subtle. Technically, gravitational energy is shared between the Earth and the ball. However, because Earth has so much mass, and because of Newton's law, there's the same amount of force, it has effectively 0 acceleration or speed as the ball is falling. Basically, the ball is the thing we see accelerate. So unless you're lifting something as crazy large as the moon or something close to that, we can pretty much assume the Earth remains motionless and ignore any motion, ignore any energy associated with the Earth. So very oftentimes you'll say the ball has potential energy. What I'm trying to tell you right now is the ball does not have potential energy. The ball shares potential energy between it and the Earth, itself and the Earth. However, who cares? All right. So we're going to misspeak and deliberately say the ball has gravitational energy all the time. Just being clear, that's not strictly speaking true. Chapter 14 will address that. Now, we're going to talk about conservation of energy. E initial is equal to E final. That's what a physicist means by conservation of energy here. Okay. So when the initial quantity of something equals the final, physicists say that something is conserved. You could talk about charge being conserved, mass being conserved. There's a thing in physics called strangeness. Strangeness could be conserved. So there's all kinds of different properties. That's great. Charm is conserved. Yeah. All right. Let's go on. Now, I like to think about energy in terms of money a little bit sometimes. So let's go through this on page 14. Suppose you have checking and a savings account at a bank. So 2 different accounts. You have some money in both of them. So those accounts could be your system, your financial system. We could view the savings account as potential energy and checking as kinetic, or vice versa. It doesn't really matter which. The idea here is you could transfer money back and forth between your savings and your checking account, and you still have that money. So that is an internal transfer, right? So it is totally possible to transfer energy from potential to kinetic without losing any. Now, here's where things get tricky. If you purchase something, money leaves your system. If you get a paycheck and you deposit it, money is added to your system. And so in the real world, energy is not always conserved. Money is not always conserved, right? Most often, money is leaving our bank accounts. So unfortunately, we usually have losses. Now, we could think of this as in chapter 8, this might be a model of this. Okay, so let's take a look. You got the entire universe. Okay, the entire universe is here. And what we're going to do is look at some subset of that universe. And that we're going to call the system. And what happens is there could be some spring energy. There could be some gravitational energy stored between the Earth and these blocks. Okay. Whoops. Now, you could have internal forces. And then there's also external forces. Okay. So maybe there's friction that causes heat, causes the table to heat up. And then once the table is hot, it radiates infrared radiation out into space, and we lose it from our system. So what happens is in a real world system, there's going to be some stuff we can control and then some stuff beyond our control. And we say the stuff inside our system, if it's conservative, that stuff should conserve energy. So E initial should equal E final as long as these non-conservative and external things do negligible amounts of work. So what we could do is we could figure out the work done by friction and figure out the work done by the space zombie. And so when we add up the work done by the friction and the space zombie, we would then say, okay, we got this piece of the puzzle, and say, other than that, energy is conserved. All right. Note, if you needed to, you could draw an FBD, do work just like we did in Chapter 7 methods, and get each of those terms in that non-conservative work. Now, notice what we will be doing for gravity or for the spring. Instead of doing work calculations, we're going to use some formulas. I'll show you those in a minute. I want to pause. Any questions on this? Okay, I'm plowing on. You can, if I didn't give you enough time, please unmute anytime and just shout at me, say, dude, what's up? Okay. And we're going to get to the summary on the next page. What did we do in the last chapter that was different than this? What we said was the network from all the different forces is equal to the change in kinetic energy. And it turns out this, remember, if you just take this work done by gravity and change that into a negative delta U due to gravity, it would flip over to the other side and you get this chapter 8 problem. All right. So it's the same stuff. So here's the summary. What is the takeaway from all this blather? Okay. In the entire universe, E initial should equal E final. However, it's impractical to measure the energy associated with atoms on Mars or Jupiter or things in another galaxy. It's unrealistic to say energy is conserved for a lot of problems. So in many real life systems, there's work done, right? Because energy will leave our system, and our system is not the entire universe. So as a result, we have to do this kind of thing. Now, when you're doing energy problems, you either do the work done by gravity and the work done by springs, or you do the calculations of potential energy, but you don't do both. Why? Because work and potential energy are essentially counting the same thing. Now, here are some energy formulas. We already talked about this MGH formula. If you're wondering about the spring formula, I don't know if you remember from last time, we said the work done by a spring was minus 1/2 kx squared. So the spring energy is plus 1/2 kx squared. This is a term we will use in chapter 10. I'm putting it here to be complete. So we don't need to understand this right now, but that has to do with rotation. And then this is translation, moving from point A to point B. Rotation is spinning about an axis. Those are different. So for now, we're still going to talk about blocks sliding and moving around. All right. For problems with sliding objects, here's the chapter 7 style. You get the work from every single force. You do this calculation. However, chapter 8 style is going to be much, much, much better. So we're going to learn this part down here and practice that in just a minute. So what we do is we say, you got all these different potential energies, and we say, okay, there's some initial kinetic, some initial gravitational, some initial spring, and some work done by friction, let's say, or a zombie rope. Then there's some final kinetic energy, final gravitational potential, final spring potential. Again, there's some weird cases here. Let's leave it at that. Finally, again, gravitational energy is technically shared between Earth and the object, but we oftentimes don't bother to say that. Okay, strictly speaking, a ball by itself. That's a lot of stuff. Any questions about that before we start doing problems? All right. Let's go to a simulation next. Okay. So here's a case. I'm going to put this girl right here at 4. And actually, let me do this. Let me have her floating in space. I'm going to hit the pause button. Now, I don't know if you can see this. Let me get rid of the grid for a second. Let me put this girl right over here. This is, we're going to have this girl rolling around on the track. And I don't know if you can see this or not, but right beneath the girl's feet, there's a red dot. This computer code is assuming the mass of the girl and all her helmet and the skateboard and everything is located right there on average. So they're assuming that all of the mass basically is located at the bottom. This just makes it easier for drawing things, okay? It's obviously false. We know the center of mass is probably somewhere up here in her stomach or something, her belly button approximately. However, if you want to, feel good about this, remember we've got this skateboard here. If you imagine that the skateboard wheels are actually 10-mile long cylinders made of depleted uranium, then the center mass is about right there. So it's just a very special skateboard that you don't notice the axis into the page is actually 10 miles long. Whatever. That's physicist humor. It's not good. All right, whatever. So the point is just assume all her mass is concentrated at that red dot. Okay. Now, let's go over here. And I'm going to put this girl, again, I've hit the pause button. That's why if I hit play, she'll start falling. So I'm going to put her right here at the 4 spot. That's the best I can do. So that's why we're using this dot, because it makes it easy to line up on the grid. And now I'm going to show this bar chart here. Right now, it's paused. All of her energy is in potential form. And again, the equation for potential energy due to gravity right here, we know that U, gravity, for right now, we're going to assume is mgh. If we want to use h equals 4, I need to assume this height is 0. And so that seems plausible. So right here at the bottom, we're assuming that height is 0. So right now, if we plug in her mass, we could plug in what g is, and we could plug in 4, and we'd get a number. If you recall, kinetic energy, does anybody remember that equation? What was that equation?
mv squared.
Yeah, good. 1/2 mv squared. Whoops. All right, so keep that in mind. So as this girl falls down, what should happen to her potential and kinetic energy? I suspect you know, but let's run it. And let me do this. All right, so let's run it. And I'll just run it in slow motion for right now. Shocking. Right at the bottom, notice her potential energy is 0 because she's at the 0 height level. All right, so we keep going. And notice it just keeps going back and forth. Great. Nothing crazy here. We see this oscillating back and forth. Let's run this at normal speed. All right. Nothing too crazy there. Got it. Now, what's going to happen if we add in some friction here?
The energy is going to go down.
So yeah, and so let's just do this. Let's kind of exaggerate. Let's put in quite a bit of friction here, and we'll show what's happening here. Whoops, let me take off the speed gauge. So as this girl is going downwards, we see that some energy is being transferred into thermal energy. And as a result, each time she comes back and forth, she loses a little bit of her max height. And so as this goes on and on, the energy is not lost. It's just lost to our system. So what's happening here, let's speed this up and let's jack this up. So what's going to happen is in the real world, this is why we gradually go to lower and lower heights. The friction is soaking up some of our energy and it's transferring it essentially to outer space, right? The road is getting hot. The wheels are getting hot. The bearings are getting hot. Once they get hot, they emit infrared radiation, and that's going to leave the planet eventually and just go into outer space. Good thing we have a sun to keep us cozy and warm. All right. So that's pretty good. So, all right, we could take that off. So that seems totally reasonable. So again, in the real world, energy should be, or let me rephrase, in an ideal world, friction would be negligible and energy would be conserved. The rider would go back to the same height all the time. So now let me go to right here. Let's go to this one. Whoops. Okay, so here what we see is I'm lifting up this pendulum and I'm going to let go of it from right there. I don't know if you can see this. Let me make it bigger. So I tried to make that pendulum level. I don't know if you could tell there's a bubble inside that level. So it's approximately level there. And so there's a weird situation here. Right here, there's a rod sticking out. So this pendulum's going to swing and it's going to hit this rod. And when it does, what do you think should happen to this mass? Is it going to go, well, let me rephrase it like this. Let's say this is a 45-degree angle, and that's theta initial, okay? Theta final. What do you expect should be true for theta final? And again, theta final is going to be this angle right here, right? How high up will this thing swing on the other side, and what will that do for theta final? Will it be bigger than, less than, or equal to 45? What's your gut tell you?
Equal to? Speed up, right?
I heard 1 equal to, what was that, Alonzo?
It'll speed up.
What do you mean by speed up?
The mass.
Okay. So when it does that, eventually, do you agree it comes to rest eventually? It's going to swing. It's starting from rest, and then it's going to swing and come to rest somewhere over here in this quadrant, right?
Yeah.
So when it comes to rest, what do you think should be true about this angle? That's kind of where I was going. Does that question make sense now?
Yeah, it does.
Yeah. All right. So I heard 1 say equal. Well, let's run it and see, because it doesn't really matter. Let's see what we get. Here we go. Notice it's about 1 inch or so below the meter stick. Notice it goes to the same height afterwards. Why does it do that? The idea here is it has initially some energy. Now down here at the bottom, we could call this the y equals 0 reference level. And so we expect it to go to approximately the same height as long as frictional forces are negligible. Wait a minute. Doesn't the tension from the string do work? What's the work done by the tension in the string in this case?
mg/2?
Nope.
No.
That was a
mg.
different problem.
Yeah.
Nope. It's not mg. Go ahead, Alonzo. What was that?
I was just gonna say that the tension got higher, I think.
Okay, I'd have to think that through. To be honest, I don't know. But what I'm looking for is you could be right. The tension probably changes because you're at a different angle. Agreed? And so actually, I think the tension, let's see. So mg's here. I think the tension actually goes down because the component, right? The components left and right are going to be balanced because at the top, AC is equal to 0. So I think the tension actually drops over here. But anyways, yeah.
Okay.
Okay.
Isn't it kind of like the problem you were saying earlier about the truck and the tree?
Yeah. Oh, that's interesting. It turns out this is a little bit different than that. Yeah, we could discuss those differences later, but for right now, I want to focus back on this one. Let's focus. What is the work done by the tension? I'll give you a hint. It's a number, and that number is less than the number 1.
0.
My God, you're good. All right. Why is it 0?
So it went to the same height? Is that?
No. Perpendicular to displacement. Remember, the tension is pointing towards the center all the time, whereas this thing is moving this way. And then if it's down here, the tension is always perpendicular to the direction it's moving, right? So the tension does no work because it's perpendicular to displacement. Let me pause and make sure that makes sense. Is everybody okay with why this is true over here? The tension obviously matters, but remember, for stuff in a circular motion, the force towards the center does no work. It just changes the direction. It matters, but yeah. All right. What I was looking at is initially the gravitational energy initial is something like mgh. The kinetic energy initially is 0. At the end, what's the kinetic energy? When it gets right up there to the top,
0.
0. And then right here, what does that tell us the gravitational energy must be? The same. Now the angle needs to change to get to that same height. So we see that theta final is bigger than theta initial. However, now again, right here, notice this is a lot bigger than 45. This looks like 65 degrees maybe, right? In the initial one, it was about 45. Whoops, zoom. In the initial one, whoops, oh gosh, that's a terrible angle. It was about 45 degrees up here. So we see that the angle has gone up, but the potential energy has not changed. Whoa. All right, let me see if this, all right. So let's just run this again and watch it. As this goes back and forth, it should go approximately the same height every time. Are there frictional losses? Sure. Is there a tiny bit of air resistance? Yeah. So in the real world, it's going to go lower and lower each time. But we see those losses are pretty negligible. It goes approximately to the same height every time. All right. Now, there was something in the chat that didn't make sense to me. I want to look at that. Now, remember, if you look at this at any point in time, the tension right now is this way, and the ball is moving this way, tangent to the circle. So there's tension, and there's ds for this small little part. And I'll draw these as vectors. If I hit play again and look at it a second later, watch it. Watch it move parallel to ds. Right? And now right here, the tension is up. ds is now this way. Whoops, that's terrible. Well, it's approximately right. Let's leave it. And again, it's perpendicular. When I run it, and so, Jacob, you might have been thinking displacement is horizontal for a small angle, but these are no longer small angles, right? Okay. All right. Other questions? All right. Let's go to the next. Let's go to the previous one. Can I get there? All right. So in this case, let me clear these out. What we have here is a high road in kind of that orangish color and a low road in that light blue color. Now, in this experiment, so just to be clear, there's a high road right here and then a low road in the foreground. So we see that there's a timer associated with these at the end. So that timer can be used to measure the velocities of the ball. I should be careful, the speeds of the ball. And those are going to appear on the screen. So notice this is the high road up top, and this is the low road down here on bottom on the timer screen. All right. Now, in this case, there are some errors associated with mounting these things and trying to get them exactly at the center of the ball. And I didn't want to spend all day, so I got them approximately close. So don't expect these numbers on the screen to be perfect measurements. That said, which ball should be moving faster at the end of the race, if you had to guess?
Same speed.
Okay, and what's your reasoning?
Well, so gravity is involved. It's a conservative force, so it's going to maintain the same energy.
Is
How
it
about go ahead.
They start and end at the same position, like the height?
Yes, and so if I could say this to both of you, they have the same delta y net. This one goes way down. The low road goes way down, but then it comes back up. So it should have the same delta y net. Remember, delta y here is the net change in height. So we expect they should be moving about the same speed at the end. Let me get the chat. Okay. So now in this case, sorry, I got a little mark here I want to get rid of. All right. So now which one should win the race? The high road or the low road?
High road.
It's an interesting guess. Now that I said that's an interesting guess, do you want to reevaluate?
They're both going to finish at the same time?
That's also an interesting guess.
Okay, I'll say the low road then.
My gosh, that's amazing. So let's take a look at this one. Notice I released them both from rest, right? There. Okay. They're going the same rate. Now notice the lower one gets down there and goes faster on that lower section. Did you see that? Let me hit play just a second. All right. So now it's not perfect. Notice the measurements of the velocity at the end are essentially within error tolerance. So if you actually count up the associate the errors with getting these things aligned vertically, we see that the speeds are actually, for all intents and purposes, the same within errors. Okay, so they do actually have the same speed at the end. The issue is when one of these goes lower, this section right here, sorry if I could cover it right here, this section right here between the flat section of the low road, that section is covered at higher speed, right? And so are all these sections here, these downward parts. So while the final speed is the same, the two do not experience a tie. So there are some issues here that are slightly different between a high road and a low road. So in general, what do you think? Is that always going to be true, where the low road is faster? What's your gut tell you?
No.
Okay, why not? Can you give me an example where it wouldn't be the same?
If the downward slope was less?
Okay, possibly. However, in this case, I don't think that would be true. But maybe in a different scenario, that could possibly be true. Because even if the downward slope is less, I think you'd still get, well, it might depend, right? So if this is the
What if it was
high,
shorter?
yeah, so maybe we get something like this, right? If you just had one of these, it would probably be closer. Agreed? Or if it was a small, rather than say like this.
What if it was like curved? Would that have?
Yeah, so ideally, if it was easier, I would have built a curved road like this, and then it would be nice and smooth, and then the balls would be less likely to skip the track. Turns out I shot that video like 30 or 40 frickin' times. Okay, it's not easy to get both balls to stay on the track because we bent them with a pipe bender and they're all jagged. So it's actually, this would be ideal, but yeah, so a smoother road might actually be a little bit faster. All right, what else? Can you think of a situation where we absolutely know the lower road would be slower?
If it had,
Go ahead.
let's say if the ramp at the end was taller.
Okay, true, but let's say we have to have the ramp at the end be the same height. What if it went down 16 frickin' miles? Wouldn't it have to take longer? The farther you go down, even if it's in free fall, this would take hours, right? Well, maybe not hours, but whatever. It would take forever if you go down very, so just to be clear here, right? What if you go all the way down to the bottom of the board, then back up? I could create a situation where even if this thing was in free fall, it would take longer to fall down than this one takes to cross the whole track. So clearly there's some optimal path here. So yeah, and in general, this is true even if you did a straight line path. A lot of people mistakenly think, let's say we're just trying to get from here to right here. The straight line path is the shortest distance, but it does not take the least amount of time. In general, there's always some path that curves like this, that takes less time and it dips lower than you might think it needs to. There's a name for this path, and it's called the brachistochrone. Now, chronos, time, etc. There's some time in there. So this is called the path of least time. Now, if you're curious, you could read about the Bernoulli brothers and brachistocrones, but they were starting to get beyond the scope of our class. It turns out, I think the old story is that one of the Bernoulli brothers was trying to figure this out, figured it out, had to invent a new branch of mathematics to figure it out called the calculus of variations, realized he was the only person that knew the answer, and then challenged his brother in public through the journals to make fun of him or something like this. But maybe that's an old story. You should trust yourself and do your own research and see if that's legit or not. But it still makes a good story that Bernoulli was taunting his brother like, haha, I invented a new branch of mathematics that you don't know about and you can't solve this problem. So anyways, it's super cool. Another weird attribute of brachistocrones is you could start two objects on the same brachistochrone at different spots. They'll both get to the end at the same. But yeah, conceptually, we could get it this way. Okay, think about it. When you put an object on here on this upper ramp, it's going to have constant acceleration the whole way, and it's going to gradually speed up across the whole path. Whereas if you put something on this lower path right here, this is going to have a large acceleration early in the motion. That's going to get it up to speed faster. And so then it's going to pick up a lot of speed early and cover the rest of the distance at high speed. And that's why this makes sense. Now, if you go too steep, then the problem doesn't work anymore because you have to cover too much extra distance and the straight line path can beat it. But yeah, normally in class, we get out some pool balls and we got a 6-footer, a 6-foot brachistochrone. It was pretty hilarious, but we don't have that right now. So we're not doing it. And I'm not bringing a 6-foot object back to my house and trying to stick it in this tiny room. Sorry, my bad. Forgot it at the lab. My bad. All right. I don't know. It's cool though. You can check it out online. I'm trying to share a screen. Slowly, Zoom will get it done. All right. So let's go back to this one here. I think we've talked about this a little bit. All right. So, go ahead. Let's see the chat here. Okay. All right. Got it. Understood. You got a private chat there. All right. All right. So let's actually do a physics problem. Let me get rid of this friction here. Got it. And let me clear this out. And let's go ahead and take this person up here. We'll put this person at 4. So now what we want to do is and I'm going to take the grid off for a little bit just so I could see things. Now we'd like to understand the speed as this person moves back and forth. And notice the speed at the points where she reverses direction instantaneously goes to 0. So let's say we want to do this problem. We got to actually learn how to do some calculations and make some predictions. So let's focus on that. So let's go back to, excuse me. Let's start with this one, 8.3. So we've been doing the simulation. So let's do this. You've got a block of mass m sliding on a frictionless ramp. Okay, so I'm going to draw this up. You can draw this up as well. Okay, so I'm just writing, okay, so this is 8.3. And then we are told frictionless, I think. Frictionless. Block negligible size, so we don't have to worry about its center of mass position. This matches up to our simulation pretty well, actually. Negligible. Okay. Okay, and we know the initial height is h. Okay. So here's what we've got. First thing, we're doing an energy problem. First thing I'm going to do, set a reference level. Usually we make it the lowest point in the problem. Do you have to do that? No. You also don't need to pass. Okay. This is advisable. Do what I say. Okay. That means this is y equals h. By doing this, we make fewer minus sign mistakes, and that means you're more likely to get this question right on a test. This is not the only correct way. It's just probably the best way. That's all. Okay, so now in this case, I'm going to write down my equation. I've got some energy associated with gravity initially. Do we have some energy associated with the spring? Wait, there is no spring. Sweet. Kinetic energy. There's some kinetic energy initial. Plus, now we know that in many problems, it's possible for energy to leave our system. So I'm going to write this in here and we can worry about it in a minute. Now, what we're saying is the initial energy should equal the final energy, except for any energy that leaves our system. This is making sense. This is chapter 8 style. In this case, the initial gravitational energy is mg, and what's the initial height? H. What's the initial kinetic energy here?
0.
0.
0. Got it. Now, let's come back to this one. The gravitational energy final. At this problem, maybe we should draw the block is down here at the final state, and it's moving this way with some speed v, final. What is its gravitational potential energy at the bottom?
Would it
0?
be 0?
That one goes to 0 on this side. And then the kinetic energy would just be 1/2 m speed final squared. Okay. Now, wait a minute. We don't have any friction, so we don't need to worry about work done by friction. I don't see any space zombies. Whew, lucked out there. No space zombies, so we don't have to worry about the work done by a space zombie. Are there any other external forces in this problem? Are there any forces acting on the block that we have not accounted for already? There is one.
Normal force?
Normal force. So what is the work done by the normal force?
Is it 0?
It's 0. Why is it 0?
Perpendicular to the. Yes.
Yeah! It's
Perfect.
placing this way. It's perpendicular to displacement. So this term is 0. Nice. Now, in this case, we've got mgh is equal to 1/2 mv squared. Oh my gosh, the mass drops out. The final equals the square root of 2gh. All right, so far so good. Sorry if that's a little, there we go. Any questions on that? All right, let's bring up the problem again and look at, I think that was part A, but let's, oh my gosh, it's so slow right now. Apologies if you're getting a lot of lag on me here. It's just slow right now. I don't know what's going on. All right. Okay, so how about this? At what height above the ground does the block have half of its maximum speed? We now know the max speed is square root of 2gh, where h is wherever it starts. So if I could go back to my simulation, let's reset this. It's starting there. We know the max speed happens at the bottom. My question is, at what height above the bottom will it have half of the max speed? What does your gut tell you?
2.
And what do you think I would say next? Exactly. I hope you've noticed that our intuition is sometimes wrong, as in pretty much every time. So let's go take a look and trust the math. It would be nice if we could trust our intuition, but we can't always. So let's take a look at this one. And to speed things up, I'm going to go to the solutions for this one. Whoa, we don't want that solution. What problem was this? 8.3, right? Okay, so let's follow this right here. We're doing part B. We've got the initial energy, kinetic and gravitational, final energy, kinetic and gravitational. Well, this one goes to 0. But now this term does not go to 0 because we're saying at what height is final speed, this maximum value, divided by 2. So instead of saying solve for V final, I say, here's what V final is. V final is half of what you got in part A. I plug in the answer from part A. I get this junk. Notice the G's drop, and we get 3/4 of the height. Get half the speed in the first 1/4 of the fall, the first quarter. Crazy, right? Now, you could also do this with ratios like this. And if you want, you could look at that one. But I think this makes a lot of sense. So I'm going to go back to my simulation here. Whoops. Crap. Here we go. And so now, first, let's run it. Okay, that's about at the bottom. I hope you agree. Notice the speed here at the bottom is, oh, let me move some zoom crap here. Let's see, 0, 1, 2, 3, 4.5. So we see that V max for this particular one is equal to 4.5. How can we check that number? Well, remember that was just, how did they get that? From the square root of 2GH. G is 9.8. H was 4. So it's basically 8 times 9.8 and square root it. So hopefully we get that number. I'm going to go ahead and punch it in as well. And maybe their speed increment, we could actually calibrate their speedometer this way, because I don't think we're going to get that. 19.6 times, what did we say? H was 4. Then we're going to square root that one. So I got 8.85. So it looks like this is probably 0, 2, 4, 6, 8. Something like that. And this would actually match up almost exactly. So they're using increments of 2, but whatever. All right. So really, this should be about 8.85. Sorry about that. Let's just round it. It's about 9. Okay. And so, oh, and let me get the chat there. Yep. Oh, thanks. Sorry about that. I'm a little slow. So sorry. Let me get my eraser. So we are actually up there at about 9 right now. So this speed corresponds to 9. And so this would be 2, 4, 6. So we're expecting right about here, about 4.5. So let's see when the speed gets to 4.5 by running this one. Right about there. And notice it's almost, it's spot on. Okay. So now obviously this is a simulation, but I could show you, we've just shown this with a pendulum. It's very similar. The physics works out exactly the same with a pendulum if you care. So that's all well and good. I think this seems pretty plausible. All right. So now, any questions about that? Any questions about anything so far? Apologies if I'm going too slow. Next time we'll go a lot faster. All right. Let's go to this one. Let's say I want this to go in a circle. All right. Now, I don't know if you could tell here, but the radius of the circle is about what? What's the radius of that circle in there? Ooh, let's put it on top of that.
2.
It's about 2. All right, and just showing you here. Oh, there she goes flying off. Okay. So she's got mad skills. No matter what happens, she could always catch up here. Now I'm going to set friction to none. And then let's grab this person here, pause this, and clear my annotations really quick. All right. So where do I need to start this person so she gets through the loop? What's your gut tell you?
Higher than the loop?
Okay. So like right about there. Would that work?
I think so.
Okay, let's find out. So she started slightly higher than the loop. Watch carefully. I'm going to hit slow motion when we get near the top. Notice she got air. Oh, but she's got mad skills. So she's totally fine. So it's not enough to be at 4.1 meters. Obviously, if we go all the way up to here and run it, she should make it through no trouble. So the question is, what is the lowest height I could use so that she actually makes it through the loop? Well, let's do a physics problem. Here it is. Okay, so if we've got this block of negligible height, we could figure out these things. And so I'm just going to point out here, what's the first thing I would do in an energy problem?
Set a reference level.
Reference level. So the lowest point is usually good. So let's say that's y equals 0. So then this would become y equals h. And obviously the part where she's going to have trouble is right here. What's the height right there?
H over 2?
Not necessarily, because we don't know what that value. H is some variable. Is there another way you could write that height?
Oh, R squared? Or
Nope.
2R?
Yeah, 2r. So, Jesse, yours may have been correct for one possible scenario, the one I just showed, but it's better to say it's equal to this because this is correct regardless of the initial height I chose. Agreed? And so you were right for one case. This is right in general. That was the subtle difference there. All right. Now, if I want to go in, I could do the problem here. And when we do this one, whoops, let's go to here. You could also do a normal, oh, whoops, I guess I kind of gave this away, but we're running out of time. What you do is you do an FBD at the top. You assume it's about to lose contact. You set the normal force to 0. We figure out this minimum speed. You do this energy problem as we've done before, and we find out it's 2.5 times the radius. So the idea here, whoops, sorry. So that's something for you to work through, but I just want to show you that I'm not lying to you here. In this case, that should be basically, if I go just below here, this shouldn't work. So it was just below 5 meters here. Oh, maybe that wasn't below it enough. So how about right there? All right. Sorry about that. At some point, we should see her start projectile motion. There it is. Whereas if we take it to just above 5, we see that it works and we're good to go. Because again, the radius here is 2, so 2.5 times the radius is 5. Now, for me, a simulation doesn't really mean that much. So it's good to visualize, but here it is in real life. So now I just want to point out here, if I could, remember this distance is something like what, 2r? So if we split this up, that is right below the cutoff. Now, in this problem, there's actually a little bit of friction. There's actually a little bit of rolling energy. So it's not perfect. This ball is actually going to roll, not slide. But this is approximately right at that cutoff radius and just below it. So I'm just going to leave those marks here, if I could, and roll it. Am I going to let go of the ball ever? Sorry, must be on slow speed. Okay, there it goes. Do you see it projectile out there? So it actually became a projectile. And now if I could speed this up a little bit so we're not sitting here all day. That's slightly above that mark, and it makes it through. Now watch this carefully at the end. Look how much energy it loses. I hit pause there, but notice I actually happened to catch it right at the max height. We actually lost a ton of energy in the real world. So I released it from right about here. So the amount of energy lost, you could actually calculate the initial and final potential energies from these two states, because you know the two different heights. Whoops, that's U initial, excuse me. This would be the change, and that must equal the work done by non-conservative forces in the real life. So if you're wondering how you might get that, that is how you could do it. All right, let me see where we're at. Holy cow. Okay, we've got 3 minutes left, and let me see if there's one more thing I wanted to say about this. Let's go to here. So, okay, you could do that problem later. Here's where we start to get fun, have some fun. Imagine you have these 3 different tracks. I hope you agree that if they all start at the same point, at the top of each of these 3 loops, the speeds should all be the same. Now, in this case, if the speeds are all the same, check, that's part A. Do you think they all have the same acceleration? Is the acceleration 0, not 0? Are they all the same? What's your gut tell you?
After
All
the,
What was that, Jacob? And then I'll get you, Alonso.
I said all 0 for the accelerations.
I'll give it to you for once, because I'm assuming you meant the tangential acceleration is 0. Great job, right? Good, good.
Oh, yeah.
Yeah. Is accelerate. Okay, so Alonso, what were you going to say?
I was just gonna say, like if it was at the very top of the loop, or kind of like finishing.
Yeah, at the very top. At the very top. Okay, yeah. So in this case, do you agree they're all moving in circular motion? Now you might say, wait, dude, some of those are ellipse, but yeah, couldn't you just draw this as an effective circle of this radius right here? And this one is moving in a tight circle? Yes, you could. So the idea there is we see that they have different radii of circular motion at the very top. And now if I do an FBD, normal force is down, mg is down. We're going to get through this problem. If it kills me, we've got MAC. Look at this. We see that the normal force is equal to MAC minus mg. Which normal force is least likely to go to 0? The one with the largest AC. Which one has the largest AC? The one with the smallest radius. Which roller coaster is least likely to kill people? Design C. That is a way to use physics to do something useful, to kill fewer people. That could be useful. So this, if you design a roller coaster like this, remind me to go to a different amusement park. But I know no Allen Hancock College students would do that ever. So we're not going to do that. All right, cool. Now, it's probably time to go. Let me check the time. It's time to go. In the other class, I think I did one other problem. So if you really want to, you could read about springs, but we're going to pick up on springs next time. I think the only other problem we did in the other class was 8.10. So if you look into the book at 8.10, I know it's time to go. If you need to go, get out of here. I'm not going to do it all, but this is the one.
Question, Professor?
Go ahead. Yeah.
Yeah. So for next class, we're having a quiz, right?
yes, next class is the quiz. I feel bad that the solutions went down on Sunday. So I'm like, you know what? We got nothing going on Wednesday. It's probably better to extend the deadline to Wednesday than to have to listen to a bunch of students whine. So, and there's now going to be different students whining because I changed it to Wednesday, but what can I do? Yeah, cool.
Cool. I just had a quick question. So are we supposed to jump on Zoom first or take the quiz first, or?
You can come into Zoom and I'll put you in a breakout room. That way, if you have questions, you could be right there to answer questions, or you could pop in and out if you want.
All right. Sounds good. Thank you.
You could send me emails and stuff, but sometimes the emails, there's a lag, right? So if you're on Zoom, you can get immediate answers to your question. All right. So that's, it's up to you.
Oh, thank you.
Yep. All right. So, and regarding this one, you could look at the solutions to it and follow it through, and we will pick up somewhere around there next time.